The question is, the half-life of radium-226 is 1590 years. If a sample contains 400 milligrams, how many milligrams will remain after 4000 years? Okay, let's talk about the word half-life. So half-life means if you start with a certain amount of radium-226, that reduces to 50% of the starting quantity in 1590 years. So this means we start with 400 milligrams, then in 1590 years, the 400 milligrams will come down to 200 milligrams. So let's take an educated guess of what we can expect for an answer here. So we are looking for how many milligrams will remain after 4000 years. So we know it's 200 milligrams in 1590 years. Let's go down another 1590 years. So that's like 3180 years from the start. So the 200 milligram will shrink down to 100 milligrams. We can stop there. We have to look for it after 4000 years, right? So let's about a third of this 3180. That's somewhere about 1000 years, a little more than 1000 years. Okay. So I would say maybe approximately let's reduce this 100 milligrams by one third of 100 milligrams, roughly like two-thirds of 100 milligrams, close to let's say 66 milligrams. So that's our educated guess. So now the exponential model here is A equals A naught E to the power K times T. This is an exponential decay model because the quantity of radium-226 is reducing from where it started, from the initial value. So the rate at which it decays, that's a constant K, is a negative number. It will be less than 0. And that's why we say it's an exponential decay model and not a growth model. So here we have the initial value to be 400 milligrams. So we are saying that's going to shrink down to half of 400 in 1590 years. So in the exponential model, I substituted t equals 1590. We don't know what k is. All we know is the current value will be half of the initial value. So I just represented that by a naught over 2 equals a naught multiplied by e to the power k times 1590. Okay. So now we can cancel the a naught on both sides. So now we have 1 half equals e to the power 1590 multiplied by k. We have to solve for k. So since we have this e, let's take natural log. That's log to base e, which is written as ln, natural log. So taking natural log on both sides, natural log of 1 half equals natural log of e to the power 1590k. So now on the right hand side, by the property of logarithm, log to base e, and then again you have e to the power something. The e's cancel. I mean the e cancels with the natural log, and we just have 1590k. Now I just use my calculator and just entered things the way you see here. Natural log of 1 half divided by 1590, and I approximated that to negative 0.000436. Okay, next we are going to use the value of k in the original model. So now we have a new equation that we can use to solve or to find after any number of years what will be the remaining quantity of radium-226. So now all you can see here, the original equation, I'm only substituting for k, which is negative 0.000436, and then I also substitute for 4000 years in the place of t. So now it's just a matter of computation using a calculator, and then I end up getting 69.928 milligrams. So about 70 milligrams of radium-226 will remain after 4,000 years. So that kind of comes pretty decent, decently close to our educated guess. So I think we are good.